prelekcja, ostatnia na dzisiaj. Ostatnim właśnie prelegentem będzie Mateusz Stankiewicz, który już się tutaj przygotowuje z tego, co widzę, i opowie o... Jego prezentacja ma tytuł Finger Poking the Documents, Fingerprints Search Using CNNS. Prezentacja Mateusza będzie po angielsku, a Mateusz jest inżynierem uczenia maszynowego w Egnyte. W codziennych zadaniach koncentruje się na tworzeniu komponentów uczenia maszynowego, znajdując nowe sposoby pracy, które pozwolą sprostać rosnącym wyzwaniom i wymaganiom. Sporą fascynacją darzy aplikacje do wizji komputerowej, ale zajmuje się także przetwarzaniem języka naturalnego. Wolny czas spędza majsterkując przy amatorskiej elektronice oraz grając na klawiszach. Tak więc już za chwileczkę w swojej prezentacji poznacie Mateusza, który już, myślę, jest prawie że gotowy. Czekam tylko na sygnał i będziemy się przełączać na ostatnią dzisiaj prezentację, a jest to Meetup Neural Networking, Cyber Security i Data Science w formie online ze względu na panujące warunki i sytuacje. O, jesteśmy.
Okay. Hello, everybody. My name is Mateusz, and today I will give you a short and sweet presentation about how we actually started or just created a fingerprint detector in Egnyte. But let's start with a short story. When I started working at Egnyte a long time ago, well, feels like ages right now, but it was about 7 years. They told me that, yeah, I'm a quite a decent programmer, so I could do that, or they are looking for somebody that, would be a data engineer. And I said, yeah, that sounds cool. So what would I do as a data engineer? They said, no idea, totally no idea. But it would be fun. And yeah, I try, just gave it a go, and definitely was fun. But after a few years, we created a product called Egnyte Protect. And as marketers will tell you, this is a content management platform. So it basically what it does is that it allows you to create or just to manage data that you have on your storage service and create some policies that, or just use predefined policies that will allow you to, sorry. Shit. I'm sorry, that's just, that allows you to, track how your data is used, how it's shared, who has access to it. And those policies include GDPR, so, or more American ones, because most of the clients are, American based, like HIPAA, which which are applied to medical documents. And then after defining policies, you could track what kind of documents, or what kind of information, like personal identifiable information, names, driving licenses, and stuff like that is how it's shared, how it's contained, and so on. And sometimes we got very interesting requests from our clients, and one of those requests was that my PM came to me and said that we have a challenge, not a problem, because we have challenges, not problems, right? And then he said that, can we find fingerprints in documents? And I said, like, digital signatures or what? And then, no, like a real human fingerprints. And I said, well, probably. So, but, can I get the data? And he said, no, that's sensitive. No, you cannot. So that was a bit of a problem. But what we got was a description how the data looked like. And basically that was the, those were standardized dactyloscopic sheets, all filled out. And yeah, so I thought that we could give it a try and try to build a classifier. And there is a very good tool to do that, or a very good, let's call it a tool. These are called convolutional neural networks, and they are basically created to work or to solve machine learning problems that come with images. So everything that involves analyzing images more or less could be solved here. If that's an overstatement, but we can say that's true. And to understand what we are talking about, let's split it into two sections. And first, let's talk about convolutions. So what exactly is a convolution? And the definition will tell you that the convolution is a mathematical operation that accepts two functions, returns a third function that describes how how one of the function affects another. So I think that's very telling, but mostly about people who wrote those definitions, not about the convolution itself. But fortunately, it is much easier to see, how it works, and not how it. So let's say that we have two functions, and those two functions, we slide one function over the other. So we just let's say that they are in a time domain, say, and for the values that are that are common for those two functions, they are represented as this area, this yellow area that you can see. And this common area is actually a result of convolution. So that's how it looks in 1D. Hopefully that's more or less understandable. If not, then let's move forward and let's move to 2D, right? Because also we can do convolutions in two dimensions. And what is even more fun, we can treat those not as functions, but as images. So let's say that we have the blue one is an image, and this little gray moving thing, like this 3x3 square that is moving, is actually our convolutional function. It's called the kernel. And then, after we apply this kernel to this blue image, we get this greenish image that that is, our output. And there are some, like many parameters, you can define stride. So, how many pixels it can jump, or the padding. So those dotted lines around it. So basically what to do when we run out of pixels around the image, right? But let's focus right now on the kernel itself. And the kernel is a straightforward thing. Basically, it's a matrix. And this matrix is where all the magic happens. So we were talking about kernels that are 3x3, and let's stay with that. This is an example of a kernel. And the way it works, we put the future version, future value of a pixel is actually a sum of all those operations. So we take one pixel, the one in the middle, and we multiply it by 5, and we take all the surrounding pixels, multiply them by values, and add all the values together. And that's where the magic happens. Because when we apply this one, let's take some common, and well-known image that we already saw. And this, so in the right corner, you right now have this kernel, and the output of the convolution operation will be below. So it might not be very visible, but this is a sharpening function. A fun thing happens when we invert the kernel. So we change the signs of all the values that are there. So then we have something that's called the Laplacian. And the Laplacian is another very fun term, but overall it detects or just draws high frequencies in an image. And what is a frequency in an image? That's sounds a little strange, but let's say you have a very smooth gradient of colors. And this, so from one end to the other end, this gradient would have a low frequency because there is no sudden change of colors. And then if you have changes like from white to black or from white to other color, it will have a high frequency because there is a high change between, white and black, like values of white and black. And basically what we have here is a quite simple edge detector, because on the edges of this of logo of Egnyte, we have quite high frequencies. So the result is a very nice edge detector. We can apply other functions and see what it does. So for example, if we fill all the values with the values from 0 to 1, then we get blur effect. Fun things happen when you do like when we apply something like this. This is called a Sobel operator, and as you can probably see, it just changes, like it highlights the certain borders and hides the the other ones. So from the kernel, you can see that the right borders are highlighted and the left borders are suppressed, and you can work with that on basically any side. So this is an example, like just we'll take the lower borders, right? And yeah, so basically that's what we need to know about convolutions when we start talking about convolutional neural networks. And let's move to the second part. What exactly are neural networks? So, and also what is the difference between a neural network and a deep neural network? So let's start with the simplest, the easiest, or the first implementation of a neural network. That's called a perceptron. And this is basically a building block for all neural networks, because what we have in each node of a neural network, let's call it a node or a neuron, we have some inputs. Then we apply some weights, those W1, W2, W3, and so on. We sum it up, then add some bias, doesn't matter right now. And one of the more important parts is this function, like this nonlinear function. This is a thing that we could talk 4 more hours about, because that's a thing that makes basically a neural network, a neuron, what it is. Because otherwise, it's just a linear function and it, doesn't do much, right? And so this architecture, like this one perceptron, could differentiate between two things, like let's say true, false, between one value and the other. But if we put it in a network, we get what we call a neural network. And then we can accept multiple inputs and get multiple outputs. So the question is now, why is it called deep neural networks, not just neural networks? And this is like a historical thing, because when we had those, let's call them old, like in the 70s or 80s, neural network could be as big as, like two perceptrons, so one for input, one for output. And due to computational challenges, that was enough, or sometimes it was even, more than enough. But right now, what we could have is that we have multiple hidden layers. So we have input, we have output, and then in the middle, there could be a lot of different layers, so containing multiple neurons. And every network that has more than one hidden layer is traditionally called a deep neural network. And so that's the magic to it. I think that's all about it. And when we put together those two things, then we get, maybe let's not put it together right now. Let's talk about a special version of a layer, not containing a neuron, but containing convolutional operation. So what we can do is, so this is the representation above of a RGB image. So for, we have 3 channels, one is red, one is green, one is blue. And below we have our, output of our convolution operation. And it works basically how I showed you before. Each output is computed by making some operation on this image. What is very interesting about it is that before, when we wanted to apply some operation, we had to define it first. And this is a task of a neural network to figure out what operation would be best for each layer. So what we define is the size of the kernel, the stride, so how many elements it should move, padding, so what happens when we get through the board, through the out of the image, and also how many layers or how many filters we have. Because in this picture, you have 2 filters. So convolutional operation is applied to this image 2 times, both times with different weights. And now we can put everything together and create a convolutional neural network. So the first, apart from the input, the first step or just the first part of the network is responsible for learning features. So we have all those convolutional layers, and you can, this is a standard way of building them, that you have at the beginning, you have very wide and very shallow operations. So usually very little those filters that we talked about, and they increase and increase in the, while the depth of a network increases. And what is really fun, if you analyze it, at the beginning we have very simple operations, like the one that I showed you, like sharpening, edge detection, and after that we have operations that build upon it, and sometimes they are quite surprising. For example, when you could analyze, when we analyzed a network that was, one of the outputs was looking like classifying if an image contains a bookcase. So one of the first layers was responsible for analyzing, vertical lines, horizontal lines, but somewhere in the middle we saw that neurons became activated, so they responded to letters that were horizontal, and then the next one was activated if there were much more letters than there were, multiple letters in a row. So what we, the network actually learned that you have, every book has a title on its top. So if there is lots of letters, then it's probably a book. And if there is lots of books, then maybe it is a bookcase. So it's I don't want to make it that, the neural network is thinking in any way, but sometimes you can get that impression. But after creating those features, there is this classification part, and this is basically a standard neural network. So we call it fully connected neural network. So we have those neurons that each one is connected to the other one. There could be a few layers of that, and in the end, we have as many neurons as many outputs we want to have. So for example, there is a challenge called ImageNet. This is like a competition that and the main purpose of this competition is to classify images into 1,000 classes. So neural networks that are made for this competition will have 1,000 neurons at the output. Each one will fire for a certain class, and then we have just to interpret the result. Okay, so coming back to the classifier that we wanted to build, our classifier would have a very similar structure like all other neural networks, like a convolutional neural networks, but our output would be one or two, basically, well, let's say one neuron that will say this is a fingerprint sheet with fingerprints or not. And basically that's the main idea. But to do that, we have to create a data set. And I told you before that we didn't have any data from the customers, so that was a bit of a problem. But fortunately, they were using standardized sheets. So we found out a data set that contained high-resolution images taken from those sheets. And there were like 4,000, I guess, for each finger. So it's called NIST Special Dataset number 4. Right now, I think it's discontinued, and some new datasets are, like more modern because they look like they were taken in 60s or 70s and then scanned. But there are some more modern, like machine gathered datasets that are now available. But with this dataset, we were able to take those sheets, basically from EU pages. The EU publishes, for example, sheets for Interpol or just or other law enforcement agencies. And with some Python magic, we were, because we knew the positions, we were able to mix one with the other and create random sheets with fingerprints. Having that, we created around, well, we had 12 sheets and we created 4,000 documents for each sheet. So about 48,000 documents overall. And then we also had to create another class, which was, non-documents or just or even documents, but not contain just normal documents, not fingerprint sheets. And to be honest, this is one of the single moments that my collection of funny images was useful, because the more diverse images you put, I think the better. And yeah, so right now, and you want to aim at having more or less the same number of documents in both classes. So you wouldn't get skews or just biases towards one or the other class. And obviously I haven't had 48,000 random documents, but I think that's the easiest thing to find on the internet right now, just random images. And also the approach that we took is like a standard approach in the industry. And from the practitioner's point of view, you don't want to build your own neural network, like your own architecture, you train it and so on. What you want to do is use a technique called transfer learning. And transfer learning is basically taking other network that has pre-trained weights. And it's quite important because researchers found that if we take another convolutional or just another network, it doesn't matter if that's convolutional or not. It also works very well for language models. And then those features that were trained on those images are actually transitive to the other types of tasks. So for example, if we have a network that is able to classify images into 1,000 other classes, then we can take it and apply it to, let's say, finding cancer in X-ray images, and it works quite well. So this is basically what is being done in the industry right now. What you do is take and also what is very important is that you don't have to have such a big data set. So for example, ImageNet challenge that we were talking before is about 17 million different images, and that's a lot of data. And for example, training a language model could take gigabytes of text data. So training one would take weeks if then on a good day, or if you have like lots of machines, then maybe, but it's still very expensive. So you take this network, you just delete the last layers that are responsible for this classification, and you put your new ones. So for example, in our case, we took ResNet, and ResNet is a very popular network architecture, like a convolutional network architecture. And this one was actually trained on ImageNet. So it had 1000 neurons as an output. We deleted that, and we created this one neuron for our output and some fully connected layers before. We froze the feature layers that were there and only trained the layers that were at the end. So this is actually quite disputed, and this is I didn't find much data about what is the correct way to do. It's more like a rule of thumb that if you have a lot of data, then you can try fine-tuning whole network, so you don't freeze those. You can train the whole network. But if not, you can try just getting train only those few last layers. So basically that's what we did, and let's move to the results right now, and let's start with some performance results. And this is the inference. So the time that our neural network takes to process the document, and when we use GPU, it is slashed 100-fold. So in this case, when we had some preemptible VM machines in Google that were using NVIDIA K80's GPUs, actually processing time wasn't the problem. The transfer was so much, so much bigger cost to us, in terms of computing speed, that we could just omit the processing speed, but about the other metrics, we had about 1800 images, almost 1800 images in the test data set, split almost half by half. And what you see here is that we got 20 false negatives and 79 false positives. So it accounted to about 94% accuracy. So quite good, right? And we also thought that, and we put it in production. And what we saw is that it was mostly okay, but we had some problems. For example, these kinds of documents, so empty sheets, templates, were also detected as sensitive documents with fingerprints. And that's not what we wanted to achieve, right? So what we learned from that is that our neural network didn't learn how to detect fingerprints. It detected how to recognize sheets that, like the geometrical structure of the sheets that, usually contains fingerprints, but that's not the case in the case of our client. And this is a very good representation of garbage in and garbage out rule in machine learning, because what we have here is that we don't it's not exactly garbage, because we got some very nice results and it mostly worked for our clients in production. But our expectations was something different from what the neural network actually learned. So you have to be very careful, what actually comes into your data set. So in order to fix that, we thought of 3 things. And the first thing was the easiest one, and we just added those empty sheets to the false data set to somehow force the neural network to see that it's not what we are looking for, right? But we had like 48,000 documents, and then we had 12 sheets, so doesn't really, it doesn't give the chance to, to learn what we are going to convey. So we had also another ideas. One of the ideas was to augment the images. So this is a very nice technique to improve, or just the idea of augmentation, or just the results that we want to achieve is that, one, we want to have a bigger data set. So neural network have more examples that it can learn on, and also it could generalize better. Because what we do with the image is we make all those operations like, blurring, sharpening, we rotate it, we change colors, we mirror it, we delete parts of it, and then it's still, you can still see that this is a kind of hamster, but like if you show only one image of a hamster, to the neural network, it might not find hamsters in every possible configuration, or with different ears, or with different nose, different position. And this is a way to learn, like to teach the neural network how to perform better in other situations. But in our case, it's we didn't want to distort the fingerprints too much. So what we did is that we added a random rotation. Also, I don't know if you can see here, but this image is slightly blurred with a little noise. So more like a scanned document. And we also did this for those empty sheets. And third thing that we did for the false, let's call it false, or just a non-fingerprint data set, we added sneaky documents, as I call them. So there were the same sheets, but with some noise instead of fingerprints. And it actually worked quite well. The rule of thumb that I applied here is that if a person can differentiate between noise and a fingerprint, then neural network can do at least the same. And after that, like no more trouble for us. The accuracy stayed more or less the same, but that's because our testing data set wasn't very robust in this way. So it also contained only very small number of those sheets. So it still is around 94%, maybe with some decimals. But we stopped having this issue. And so that was our first approach, actually. And then when another customer came, they told that, okay, we have this fingerprint detector, but they have documents that are signed with fingerprints, and it doesn't really work for them, because almost none of the documents are being detected. And that's true, because we were aiming at those dactyloscopic sheets, and the neural network most certainly learned the structure on how it should look, and it is not looking at certain fingerprints just in every document. So that was our next area of improvement, and actually it still is, because what I'm showing you is a little bit of teaser, and what we are trying to do right now. So the idea is that we could treat fingerprint detection as object detection problem. So there is a very nice algorithm called YOLO, and the name comes not from the usual abbreviation, but that you look only once. So this is an algorithm to detect objects, usually used for like detecting objects in real world, like in a street environment. And the biggest advantage is that it's very fast, because to detect all those objects, it needs only one pass of convolutions through the image. So it is for small images you can get what around like real time object detection, so it could be implemented in some smart cars applications and so on. But how it works is that we divide the image into grid, and each grid is like it gives a candidate for an object. So let's say that the yellow grid detected that this is a person, and the blue dot is the center point of this person, of this bounding box. But also we can get it also proposes what is the bounding box itself, so it can get it could get bigger than the grid itself. And each grid does that, and after that we have propositions, and we could get lots and lots of propositions. So we need to have some way going from the middle situation to the expected outcome. And in the training environment, what we want to teach neural network is that those are the objects. So for a loss function, like I wasn't getting into loss functions so before, but well, basically what the loss function tells us how good the neural networks fares, or just how well it is taught or learns the problem. And what we can do is create the intersection over union. So this is a number saying that this bounding box is quite good for this particular object or not. And 1 is best, 0 is worst, and usually we leave only bounding boxes that have IOU bigger than 25 or 30%, depends on an application. So what we wanted to do is that we wanted to apply these algorithms for fingerprints, and this is the approach actually is very similar to the previous one. We take pre-trained network, we slash the last layers, and then we retrain it, but for just one label, just to find fingerprints. So it should look like this. So we have the documents. We need to label each and every document. So that's it's hard to generate, but we also found a way. But and we put we input the position of each label to the neural network, and it learns on that. But we are still talking here about the proof of concept, because this is work in progress, and I'll be happy to share results with you when it's finally done, and hopefully it will be during the next quarter. So thank you guys. That's all that I had for you, and if you wanted to contact me anyway, this is a page where you can find all the informations, how to get in touch. Basically that's it, because that's nothing else you will find there. But again, thank you very much, and if there are any questions, then I'll be happy to answer.